Greetings. So, we begin a discussion on classical electrodynamics, and I am sure you have studied these topics earlier. So, this is the work of Coulomb, Gauss, Ampere, Faraday, Ohm and Kirchhoff, Lenz. And as you rightly pointed out, the picture of Maxwell is missing here, but it will come. So, these are the brilliant experimentalists who laid the foundation for the theory that we are going to learn about, which is Maxwell's theory. And that in turn laid the foundation for something else, which you can see in this quotation, that the special theory of relativity owes its origins to Maxwell's equations of the electromagnetic field. So, the semi-empirical laws of Coulomb and Ampere and Faraday, Lenz, Kirchhoff, Ohm, everything, Henry, it all comes together in Maxwell's theory, and Maxwell's theory itself laid the foundation for the special theory of relativity. And this person goes on to say in this quotation that since Maxwell's time, physical reality has been thought of as represented by continuous field. And this is a brilliant idea, that the idea of field. This is a very important idea which continues to be studied even in today's physics. This is not capable of any mechanical interpretation, and this change is the most profound and most fruitful that physics has experienced since the time of Newton, and the person who said this is none other than Einstein himself, who attributes the special theory of relativity, the origins of the special theory of relativity, to Maxwell's equations. So, the field is a brilliant idea, and today we talk about it very easily. We talk about the gravitational field, the spinor field, the quantum field, the tensor field, the Higgs field, all right. But it has a troubled history. It is not something that was discovered and understood very easily in physics. Kepler and Newton, they struggled to explain how sun's gravity influenced the motion of planets. So, what is the mechanism? If I want to move an object, I stretch my hand and move it. And sitting over here without touching it, how do I move it? Right? That is how the sun, moves in some sense, the orbits, the planets in orbits around it. So, Kepler even thought that there were some invisible spokes which ran from the sun to the planet, and these spokes were driving the planet just like the wheels of a bicycle are turned by these radial spokes. So, at the time, the idea of a gravitational field did not exist at the time of Kepler. And then we talked about the velocity field in fluids. Euler used this. In fact, they went on to study, Euler and Lagrange went on to study the divergence and curl of the field. But even then, the velocity field itself consisted of particles which were the fluid particles which were moving, all right. Whereas a field as such exists, even if there is no material particle at that point, if I have a charge over here, it generates a field at this point, and it does not need the presence of a material particle over here, which is not the case in the velocity field in a fluid. So, the idea of a field really matures only in the electromagnetic theory, in the theory of electrodynamics. So, matter need not reside at a field point, and all of them, Kepler, Newton, Euler, and then the contributions of Coulomb, Ampere, and so on, Oersted, they all made extremely important contributions to the development of a field, but the idea of field itself was formally organized in the work of Maxwell. And Maxwell specifically went on to declare that the theory I propose may therefore be called a theory of electromagnetic field, because it has to do with the space in the neighborhood of electric or magnetic bodies. So, it is in the region around an electric or magnetic body that a field exists. Maxwell's theory provides the divergence and curl of E and B, as I am sure you have seen these equations earlier. So, but we will also be introducing the divergence and the curl of E and B in this course, and we will also discuss the same. And the reason these equations are so important, because the equations of curl and divergence for E and B together with appropriate boundary conditions give you everything that you need to know to solve problems in classical electrodynamics. The reason is that once you have E and B, you can construct the force acting on a charge, whether it is at rest or moving, that force being given by the Lorentz force. And once you have the force, you can describe how its equilibrium changes, at what rate it changes, solve the equation of motion and get its trajectory and solve any problem in electrodynamics. So, there are two important theorems which we shall be studying, the uniqueness theorem and the Helmholtz theorem in this context. But prior to this, we will briefly review the empirical laws of the electromagnetic fields. Okay, these are formulated by carrying out experiments, and the experiments give you some systematic results. Every time you do the same type of experiment, you get the same type of result. And if the result is independent of the size of the charge, means you do an experiment and estimate the force of attraction or repulsion between the two charges, depending on whether they are unlike charges or like charges. And then you find that they exert a certain force, you are able to measure the force, and you discover that this force must reduce as the inverse square of the distance, regardless of how far you keep these charges from each other. That law applies for this distance and also for this distance and also for any distance. It also applies for any charge, for a tiny charge and a large charge, or both large charges, right. So, regardless of these things, the same law works, and this is how, by carrying out experiments of this kind, that the laws were formulated by Coulomb, Biot-Savart, Oersted, Ampere, Faraday, Lenz. So, these are the laws which are the empirical laws based on experimental observations. So, these were great experiments, systematic experiments, carefully done experiments. A lot of hard work has gone into this, to do this experiment systematically and to discover from these your observations that there is a law. Okay, so, extremely careful experiments done hundreds of times, so that you can really discover a law and an underlying physical law in it. And all of these laws, whether it is Coulomb, Biot-Savart, Oersted, Ampere, anything, all of these, Faraday, Lenz, everything comes under the general umbrella of Maxwell's equations. So, we can even begin this course with Maxwell's equations and then say that all of these results are already contained in the physics of Maxwell's equations, and through backward integration accommodate them easily into our discussion. So, that is one way of doing it. So, we will not spend too much time on these laws because they are an integral part of Maxwell's theory, which is what we are going to discuss. But nonetheless, we will overview these laws. They are brilliant expressions of the efforts of people like Coulomb, and you know that if you have charges at a certain point, then it exerts a force which is the electric force, and this is what we call as the Coulomb law, which goes as the product of the charges and the inverse square of the distance. It is a radial force, so it is along the line joining the two charges, and it is this force is toward each other if the charges are unlike, and away from each other if they are like charges. And there are two kinds of charges, one that you call as positive, the other that you call as negative. And then there is a proportionality, which in the SI units involves the 1 over 4 pi epsilon 0 being the permittivity of free space. So, here this is what you call as the source point. The source point need not be at the origin, the source point is here, the field point is here, and you can have a coordinate frame anywhere, and we will denote the source point by the primed r and the field point as the unprimed r in the frame of reference situated at the origin. So, this will be our notation, that the field point is always denoted as unprimed r and the source point as r prime. The principle of superposition holds, which means that if there are a number of charges, then you need to sum over the corresponding intensity. Okay, intensity is a force per unit charge. So, you need to sum over all of them, but the sources may not be discrete point charges, they may also be continuous charge distributions, in which case you have exactly an identical expression, with the difference that you need to integrate over the source region. So, rho r prime is the charge density at a certain source point r prime, but the source point r prime is not unique, it is spread over a certain region, it may be over a region of space like this, all right, and then you need to integrate over the entire region so that you can add up the effect. So, essentially this is the principle of superposition, because it is essentially a force and forces are additive. So, now we have used the inverse square law. Now, we must ask ourselves, how do we know that the force goes as 1 over r square? What if it is 1 over r to the power 2 plus epsilon, where epsilon is some tiny number, or maybe minus epsilon, right? How accurately do we know the inverse square law? Is it only determined by how accurately you measure the measurement? Are there any other fundamental considerations involved in this? So, the inverse square law, this being a conservative force, is derivable from a potential. So, it is the negative gradient of the potential, which is 1 over r. So, the negative gradient of the potential gives you the 1 over r square, and you get the appropriate sign. Okay. But then, if the potential is not exactly 1 over r, it is 1 over r to the power 1 plus or minus epsilon, or maybe some other function of 1 over r. Then of course, its negative gradient will not give you the 1 over r square, it will give you something else. So, the idea of the inverse square law is connected to how accurately you know the potential to be given by 1 over r. And let us, for the sake of example, consider a potential which is not 1 over r. So, we consider the Yukawa potential, which is e to the minus r over lambda, where lambda is some length scale, okay. And if lambda is infinite, then you will get e to the 0, which is 1, and you get the 1 over r potential, which is the usual Coulomb potential, the 1 over distance square force, right. So, lambda is some length, but what length would be appropriate to be used here? Okay, so, you can think of some length which is made up of fundamental constants. So, a length which is made up of fundamental constants is h over mu c, where mu is the rest mass of the photon, because the photon is the one which is the virtually exchanged between two charges to bring about the interaction between the two charges. Okay. So, you have a length, a fundamental length scale which suggests itself is h over mc. H is the Planck's constant, c is the speed of light. Those would be the appropriate, fundamental constants to be used, mu being the rest mass of the photon. And if the rest mass of the photon is 0, then this lambda would be infinite and you would get the 1 over r potential. Okay. In other words, the 1 over r potential or the inverse square law is intimately linked to how accurately you know the rest mass of the photon. If the rest mass of the photon is not exactly 0, then it will impact the 1 over r potential. Okay. So, these two questions of the potential being 1 over r and the mass of the rest mass of the photon being 0, these two are tied up. It is the same question. Okay. One affects the other, and these are really not separate questions, and the confidence with which we can say that the two charges exert a force which goes as 1 over distance square is exactly the level of confidence with which we can claim that the rest mass of the photon is 0. Okay? And there are experimental tests which have been carried out on the inverse square law, a large number. So, these are extremely important questions in physics. They impact our understanding of the mass of the photon. There is a very nice review in Reports on Progress in Physics, which I have referenced over here. You might want to read it. And then of course, there is the uncertainty principle, and that puts an upper limit. And one can say that, okay, the rest mass is certainly less than 10 to the minus 66 gram. Okay. Which is almost 0, but you can't really be sure that it is 0, and it is important on whether or not it is 0, because if it is not 0, then we have seen that it impacts the Coulomb law. So, suppose there is a tiny mass which is very tiny, but not 0. If it is not 0, no matter how tiny it is, it will make the speed of light dependent on wavelength. There will be a very small wavelength dependence. So, when we now talk about the speed of light to be c, we say it is the same for every frequency, for every wavelength, right? For every wavelength it is the same. But if the mass of the photon is not, the rest mass of the photon is not 0, then it will make the speed of light wavelength dependent. It will impact the Coulomb's law and the Ampere's law. It will predict the existence of longitudinal electromagnetic waves. So, many things come as a consequence of this. And then you will have the Yukawa type potential and magnetic dipole fields and so on. So, there are very important consequences of this very tiny mass. So, one has to study them in some details, all right. So, these are the issues which are related, that does the potential go as 1 over r, or it goes as some other function of the inverse distance or whatever, right. And this is going to impact the what we commonly call as the inverse square law, and we see that it is connected with the rest mass of the photon. So, we have seen that a charge generates an electric field, and that electric field is nothing but the force per unit charge, the force being given by the Coulomb's law, right. And once you have this field, we can determine what is the surface integral of the intensity, which is the force per unit charge on a closed surface. So, suppose you have a charge at the center and you construct a sphere, a spherical surface with this charge at the center. So, can you quickly determine what the surface integral will be like? So, the intensity goes as 1 over r square. The area of a surface element also goes as r square, it is r square d omega, right. And then you will have the 4 pi coming from that integration. So, you can do this integral quite quickly. But then if you have an object, a surface which is not spherically symmetrical, then how do you determine the surface integration? All right, because now you cannot use the symmetry to determine this r square d omega factor, but actually you can, because if you look at this figure, right. So, this is a shape, this is an arbitrary shape of the surface, this is not particularly spherical, a charge is placed inside the surface, and since the shape of the surface is completely arbitrary, there is no particular symmetry position inside the surface that you can talk about, and the charge can be just about anywhere. And if you take a small surface element, then if you draw a line from the point charge to the surface element, we will think of these surface elements to have an area which in the limit shrink to 0. So, these are tiny surface elements, and the force that will be exerted on a test charge over there will be along the radial line. So, it will be along the unit vector u that you see in this figure, but the normal to the surface at that point will be the radial, will be the direction which is orthogonal to the surface at that particular point, and this will change from point to point. So, that surface orientation at that particular field point is along the unit vector r n, and the angle between them, as you see in this figure, is xi. So, now you can see that the solid angle subtended is ds cosine xi over distance square. Okay. So, now you can evaluate the surface integral, because now you can factor in the cosine xi term, okay. And once you have the cosine xi term, then you once again find that it will give you that 4 pi, right, and you will see that it gives you the q over epsilon 0, just as it did when you had the charge at the center of a spherical this thing. So, the surface integral E dot ds equal to q over epsilon 0 is true for any kind of surface, not just for a spherical surface, okay. And it is as good as the Coulomb's law. You can see that it has got in it the complete content of the Coulomb's law, okay. It is completely equivalent to the Coulomb's law. So, this is sometimes called as a Coulomb-Gauss law, because using the Gauss's divergence theorem, you can write this surface integral as a volume integral, okay, of the divergence of E. So, this is true even if the shape of the surface or shape of the region is such that it has got some kind of bays and peninsulas. Okay. So, if you see that you have got a charge which is kept over here and the closed surface is this surface which is shaded, all right. And if you look at this cone, then it cuts this surface over here, it is outward, the unit normal is out of the surface, here the unit normal is into the or toward from left to right, here again it is from right to left. Okay. So, this right to left and this left to right, the flux over here will cancel each other and there is only one that remains. So, even for a complicated shape, the law holds good. And if the charge is placed outside that closed surface, for example, in this figure over here, it is outside the closed surface, then you can see that here the unit normal is pointed from left to right and here from right to left, and the flux over there will cancel and the charge which is enclosed will be 0. Okay. So, it works not just for a spherical surface. So, one tends to think that okay, you can use this Gauss's law only if there is a symmetry for the placement of the charge, and if there is no symmetry, then the Gauss's law cannot be used. So, that is not true. I mean, you can use it no matter what it is. It is a fundamental law. It is as strong as the Coulomb's law. There are no limitations on it, all right. And using simple geometry by taking the projections of the surface and doing elementary solid geometry, you can see that it is as good as the Coulomb's law. The charge enclosed is nothing but the integral of the charge density. So, if you now look at this equation, which is the Gauss's law, which is the Coulomb-Gauss law, right, you have got a surface integral on the left and a volume integral on the right, but the surface integral on the left, using Gauss's divergence theorem, which we have used in fluid mechanics, can also be written as the volume integral of the divergence of E. So, now you have the volume integral of the divergence of E equal to the volume integral of the charge density. That is of course, the 1 over epsilon 0 factor. And these two are volume integrals, these are definite integrals over exactly the same space. So, all the limits of integration of all the three variables which are involved in the volume integration, they correspond to each other on the left hand side and on the right hand side, and that guarantees that the integrands themselves must be exactly equal. And if the integrands are exactly equal, you can write the Coulomb-Gauss law as divergence of E equal to rho over epsilon 0. So, these are the differential and integral forms of the Coulomb-Gauss law. Okay. And it is interesting to check out if this really works. Okay. We have got it from physical arguments, but let us do a little bit of elementary vector calculus and find out if the divergence of E actually gives us rho over epsilon 0. So, you determine the divergence of E. Let us use the spherical polar coordinates. We know what is the expression for the gradient in the spherical polar coordinates. So, you write the expression for the gradient and also the electric intensity vector in the spherical polar coordinates, and step by step you work out this. This is not just a dot product of two vectors, it is a vector operation. Okay. So, you have to carry out this operation. The operation involves not just the vector algebra, but also differential calculus, because there are derivatives that you have to take with respect to r, theta and phi with appropriate scaling factors, which is 1 over r for the del by del theta and 1 over r sin theta for the del by del phi. So, you have to do this systematically. So, let us do it step by step, all right, and I will let you work out the details. And once you work it out step by step, what do you get? You get the derivative of ER with respect to r, then you get the derivative of the unit vector ER with respect to theta, and these unit vectors are not constant vectors in the spherical polar coordinates. So, you have to take that into account carefully, and once you do that, then you have the derivative of the unit vector with respect to theta is orthogonal to ER. It is actually along E theta. So, you get E theta dot E theta, and you get a contribution ER over R from here. Okay. And when you put in all the terms, you find that the divergence of E, if you put the values, you get it to be equal to 0. But did we not just say that the divergence of E is rho over epsilon 0? So, we seem to have a contradiction here, okay? And this must be resolved. So, the contradiction comes because of the fact that when you take the divergence of E, where E goes as 1 over r square, you are taking the divergence of a vector which is a radial vector and whose magnitude is 1 over r square. Now, 1 over r square is a very nice quantity which blows up at r equal to 0. Okay. So, you have to be very careful when you are dealing with a singularity like that. Okay. So, that is resolved by recognizing that if the region of integration includes the point r equal to 0, then you have to resolve this contradiction. Is divergence of the radial vector 1 over r square, is it 0 or is it 4 pi? Okay. So, it is 0 sometimes and 4 pi some other times, and that depends on whether or not the point in question includes if it is r equal to 0 itself, the point of origin, then of course, this relation is not valid, and that is where the Dirac delta function comes in. So, the Dirac delta function is this was introduced by Paul Dirac, and this is like it has several representations. There are 3 of them which are plotted over here. Its magnitude sort of peaks in a very narrow region, okay? And it is such a function that when you carry out an integration of a function f x weighted by the Dirac delta function, then you get the value of the function at x equal to 0. And if it is placed, if it is shifted at x minus a, then of course, you get the value of the function at that different value of the independent variable. Okay. So, this is the quality of the Dirac delta function, and it has got a spike, and using this, the divergence of the vector 1 over r square, the radial vector 1 over r square, is 4 pi if the point includes the point in consideration is r equal to 0, and it is not 0. Okay. So, once you define the divergence of 1 over r square correctly in terms of the Dirac delta function, and there is no way of doing it without the Dirac delta. So, this is a sharply peaked function over here over a very narrow width, and I am sometimes reminded of what is called as an expert function, that an expert is one who knows more and more about less and less. So, the peak increases and the width decreases, and in the limit he knows everything about nothing. So, the Dirac delta is somewhat like that. Okay. So, you can handle this conflicting results that we got the divergence of E equal to rho over epsilon 0 using one argument and equal to 0 using the other argument, is only because we had not factored in the Dirac delta. Once you factor it in, you get a very consistent relationship, and you are able to interpret the Coulomb-Gauss law without any difficulty. Okay. So, this is a generalized function which was introduced by Dirac, and then Lawrence Schwartz proved it. Temple showed how simple it could be and how it can be used. So mathematically it belongs to the very rigorous family of what are called as generalized functions or distributions. Then there is also the Biot-Savart law, and it tells what is the value of the magnetic field at a field point. So this is the field point due to a current, and the current is flowing in a certain circuit, okay, and it generates a certain influence which we call as the magnetic influence, and subsequently we will learn that this partitioning of this influence between an electric field and a magnetic field really depends on the observer. There is a certain relativity that comes into the picture. Okay? So, this is a certain influence, and if you extend this argument of the Biot-Savart law, then you actually get the Ampere's law, and this is something that we will discuss. All right. So, this is the important Biot-Savart law, that the influence an electric current generates at a field point. Okay, the field point is R1, no, the field point is R2, the field point is R2, the source is a current at R1, the source is a current which is flowing through this, and with reference to this coordinate frame of reference, a current segment over here delta L1 is at position P1 in the current loop, okay, and this exerts a certain influence which is given by the Biot-Savart law, and if this current is a volume current, then you have to carry out the corresponding integration over volume. But then if you want to interpret this very rigorously in terms of the causality conditions, that a certain cause over here determines an effect over there, and then you take into account the speed at which this influence can propagate. Then you have to take into account the retarded potentials and so on, and these retarded integrals can be factored into the electromagnetic theory in accordance with the principle of causality, and you get mathematical equations which are known as Jeffy-Manco's equations, which you can read about in various nice books on electrodynamics. There is a nice article in the European Journal of Physics 2004 which I would like to suggest for this. All right. And all this work is understood in the backdrop of the semi-empirical laws of electrodynamics, which were developed by Coulomb, Ampere, Ohm, Kirchhoff, and so on. So, the Ohm's law is that if you have a DC circuit, then if you put a load in this circuit, then the voltage drop across the load is equal to the product of the resistance and the current. Okay? So, this is the Ohm's law, and then there are two Kirchhoff's laws, that the sum of the currents at a node, the ingoing currents and the outgoing currents, they all add up to 0, whatever goes in goes out. So, this is like a conservation law. All right. So, this is Kirchhoff's first law, and the second law is the voltage law, that if you add up the voltage across different circuit elements in a DC circuit, then they add up to 0. So, this is the backdrop of the empirical laws which were understood, and then of course comes the work of Faraday, Henry, and Lenz, in which they talked about influences being generated even if there was no traditional DC source, but a DC source like a battery. Okay, so there is a chemical reaction that takes place the Voltaic kind of battery, right? And that would generate a source of voltage difference, and that in a closed circuit will give you on addition 0, which is Kirchhoff's second law. But then when you do not have such a chemical source of battery, even then you may have certain voltages generated across different circuit elements. You may have currents flowing, and that comes because of certain induction phenomena which were discovered by Faraday, Henry, Lenz, and these are the laws of electromagnetic induction. So, the development of the semi-empirical classical electrodynamics is the coming together of brilliant experiments, and physics, as we know, is essentially an experimental science. So, you carry out careful experiments, repeated experiments, and no matter how many times you repeat this experiment, you are able to come up with certain commonalities, and these commonalities are what you call as the law. And this is the law which you have discovered through the process of carrying out careful experiments. So, such laws are called as semi-empirical laws. So, the laws that we discussed in this class, the Coulomb, Gauss law, the Ampere law, the Biot-Savart law, Faraday's law, these are all essentially semi-empirical laws. And I will continue from here in the next class. If there is any question, we can certainly discuss it. So, there are these fine subtleties about how the inverse square law is connected with the question of the mass of the photon, okay? And these are very challenging questions, and these are studied at the very frontier of physics. So, it is nice to be aware of that and apply your minds to it. Thank you.